So, I believe we can start. Hi, everyone. Welcome to our fourth Cloud Native Lithuania meetup. And today on stage, we have a few speakers. It is Zilvinas and Avishai. Welcome on board. Okay. While this is fourth, our Cloud Native Lithuania meetup, this is first one online. So we hope everything will go smoothly. And today we are going to cover two topics. And at first, Zilvinas will talk about affordable Kubernetes with spot instances. And later, Avishai will introduce queuing theory. But before we are going to jump to our presentations, this is first time when we have someone named developer advocate on the stage, and it is Avishai. So I would like to ask Avishai to share what does it mean to be a developer advocate.
Okay, so developer advocate is a role that exists primarily in companies that market or integrate with developers. So I work for CWD, which is a company that creates a high-performance database. And because our users are developers, much like yourselves, so we have a developer advocacy, which is like my department. People are responsible for communicating with the community and basically getting feedback from the community, introducing our database and technology to the community, and of course participating in meetups and conferences just like this one. You can think of it as a kind of a technical product marketing, but we also deal with a lot of technical projects designed to make our technology more accessible to developers, like we work on drivers, tooling, and guides, documentation, and whatever is needed to communicate and make developer experience better.
Okay, so thank you for sharing.
Sure.
We will be able to hear more about it later. And now we can start with Zilvinas' presentation. So thank you, Avishai, and Zilvinas, you are on stage.
Sure, give me a second, trying to share screen. Can you see my screen?
Yes.
Yes.
Okay. Okay, so this topic is affordable Kubernetes on spot instances. So the aim of this talk is not to kind of go all around explaining the whole Kubernetes as itself. It's more like trying to cover the part where it works as an orchestrator. So the very deep knowledge of Kubernetes is not a requirement for this talk. And yeah, in addition to that, I forgot to mention that I work as a software engineer at Cast.ai. So we are a company that is working on multi-cloud and cost optimization Kubernetes platform. And yeah, during most of my work, I kind of learned lots about spot instances. I didn't have much of that experience before, and the idea is just to share the basics, to share my understanding of that topic, and maybe some of you will find it useful in your daily job, or at least learn something new, I guess. So yeah, not to waste the time on introduction, I guess we can just start. So what to expect from this presentation? So the basic intro to the spot instances, some additional narrow view on the Kubernetes itself, it would be just a very small baby steps introduction to the high-level concepts. No deep dive should be expected from this part. And then we will pick up on the actual content of this presentation, which is kind of explaining the pros and cons of spot instances, like what are the challenges that you would most likely be facing if you made use of that. And we will kind of finish it up with a very short and basic demo, just showing how it works and showing it both like from the CASI application, a very simple one, and showing how it actually looks like in your AWS account. And yeah. So to start this presentation, just imagine that you have a problem at your daily work life. You are working on some nice product. There is like no upper limit on the cloud cost for the product, and you need to find a way to reduce the bill. And there is usually several options how to do that. And the aim of this presentation is kind of to talk just about only one of them, which is the spot instances. Since it's quite hard like to know if anyone will have questions during this presentation, the answers will be given in advance. So for Q&A, we will need to wait for the presentation to end, since there's quite a huge lag between the YouTube and the actual Zoom chat. So yeah, if you have any questions, just write them down. We will go through them after the whole presentation. Okay, so going next. So typically, if you are using AWS or some other cloud provider, there are usually several pricing options you have. So in AWS, there are like at least 5 of them. So one of them is like buying on-demand instances, which is, I guess, the most known one. Just basically buying an instance which you pay for on an hourly basis, and you're sure you're gonna get it. Another one is having a dedicated host, which is basically a whole physical machine which is made just for you. And then there is a third and fourth option, which is not an instance option on itself. It's basically a pricing model that you can apply on the above options. So for reserved instances, it basically means you are reserving the usage of this instance for something like 1 or 2 years. And in that kind of scenario, you are getting a discount from AWS. Or if you are picking savings plan, you're kind of saying like, I vow that I would like spend 300 euros a month, and I will get the discount of that obligation. But both free and fourth options are not something we are going to discuss in this presentation. The whole aim of spot instances is discuss the workloads that you are kind of can get rid of at any time you don't need them, and kind of discussing third and fourth options would mean that we are kind of discussing the financial lock-ins that we are kind of against of. And the fifth option is basically spot instances, which are basically the same on-demand instances, which are at the lower price range, but there is a reason for that. And during this presentation, you will learn more about that. Okay, so going next. So previously, we kind of described like the problem that you might have at your current job, such as like need to reduce the cloud bills. So in the opposite side of this problem, there's like various different cloud providers such as AWS, and they on their own have problems we need to solve. So in AWS case, we're quite a huge cloud provider. We have like lots of VMs and nodes running in their cloud, and we kind of usually have like more of them when needed, and there is a problem for them, and it's excess capacity, which basically means like whenever AWS adds something to their farm, we kind of want to make the best use out of these machines and get paid for them. So the spot instance is kind of born out of the problem for AWS, as like most of the things for Amazon. Okay, so go next. So what is actually a spot instance? So a spot instance is a EC2 instance, which does not provide you kind of reliability where you just pay money and you are sure you will get the instance and you will be able to use that at any time. The spot instances are kind of EC2 on-demand instances that can be reclaimed with 2 minutes notice from AWS. So if in the previous slide, you kind of see here that it's an excess capacity. So at the time when it is not excess capacity anymore, Amazon can just send you a 2 minutes notice and say, I will take back this machine in 2 minutes. So you should lift your workload somewhere else. And that's about that. And in addition to that, because this kind of limitation exists with spot instances, we are kind of like up to 90% cheaper compared to actual EC2 on-demand instances. But yeah, as I mentioned, the availability is not guaranteed. So it may sound like totally a bad thing, but we will get to that later, since there are like ways you can manage around that and still like have a huge discount on your billing account and that kind of stuff. Okay, so going next. So here you can see a screenshot of a tool. It's called Spot Instance Pricing History. If you have AWS account, you can just go to EC2 parts of the account and click on Spot Request and see the history options there. Basically, in the screen, you can see like that we are comparing M5 Xen 12X large machine, which is quite a huge 4K CPU on 192 gigabytes of RAM. And yeah, you can see how its price is compared to on-demand instance on an hourly basis. So discount for such a huge machine is like something for 82% here. And I took kind of a date range of a 3 months. This basically means like it was such a discount for quite some time, which kind of implies that this machine is not popular. It's been an excess capacity for quite a while, and maybe it's not used that much. So for such a huge machine, you could get such a huge discount. So this is kind of a nice case scenario. Like if you took some more popular machines, such as like C548 Lite, which is like 16 CPU and 32 gigabytes of RAM, you see like the price is a little bit different. The discount is kind of smaller, and it even like it's a little bit different between zones. Okay, so how does this actually work? Since like you have a discount, but as I mentioned before, you have a 2 minutes interrupt, which basically means your workload, even if it's a discount, can be taken away at any point. Yeah. So yeah, pricing and availability is based on supply and demand, which I said before, and yeah, the spot interruption occurs, and you need to kind of handle that, which means to kind of move your workload somewhere else. And in addition to that, we have some helper notifications from AWS, which are called rebalance recommendations, which is something that occurs before spot instance interrupt. So it basically informs that the machine is at elevated risk of being taken away. So if you saw that the price percentage was different, basically means the less popular the machine is, the higher discount you have, the less it has chances to receive a rebalance recommendation or spot instance interrupt. Okay, so looking at this very simplified view of how this supply and demand of spot instances works, you can see like at the top side, there is a demand part of the rectangle, which basically says where AWS or like other cloud provider customers, they kind of need an on-demand machine for which we are willing to pay a fixed price, and we kind of request that from their cloud service provider. Then you can see like whenever the demand is going up and like more customers occur, more of them asking for the machines, there is a whole loop where AWS would kind of would actually increase price for that spot machine that is like in other customers' fleet, and the price will be increasing until the demand is too high, and we will just like interrupt the spot machine, and customer 3 would lose that machine, and it would be given away as a on-demand machine to the customer 1 or 2, or like whoever else was checking for on-demand instance. And this is basically a loop which kind of goes always around, and the price is like for spot instances is not constant, which basically means the higher the demand, the higher the price, and yeah, that's how it goes. So going next. So in this screenshot before, you kind of didn't see the rebalance recommendation. It's kind of a new feature. So as I mentioned before, it emits an event for you on an elevated risk of interrupt. So and it arrives a little bit sooner, but it doesn't mean you will have it always. So yeah. So in addition to picking spot instances where again, lots of tools available by AWS, and in this case, I am just showing a quick screenshot of Spot Instance Advisor. So I guess most of the other cloud service providers have something similar where you could just go and list the machines available and see what is the frequency of interruption, how popular it is, what the discount you would get, and that kind of stuff. Okay. So you may ask, you kind of heard which is for spot instances that you can get an interrupt and you will lose your workloads. So what kind of workloads is it best for? So the easiest way to make use of spot instances is for anything with no external dependencies, anything that can just be easily started and stopped, such as batch processing that can track itself and see where it actually stopped and continue the work when the instance is back or when the new one is created. So basically apps that can track their progress and continue on failure, or any app on the Kubernetes or some other orchestrator that can manage that for you using some products. So yeah, this is just a quick intro to the Kubernetes itself. Just before the demo, I kind of want to do a quick digging into the concepts themselves, and then I will show more on-hand stuff. So just imagine a basic cluster, like on Kubernetes. You just have node 1 and node 2, and they're just actually running apps. In this particular case, you're running the same app as a replica on 2 nodes, basically node 1 and node 2, and just some 2 other random apps here as well. This is actually a simplified view. In the real world scenario, it's a little bit more complicated than that. It would look something like this. You would have a cluster, the cluster would have nodes, these nodes would consist of many pods, these pods would have internally running applications which are containers, and yeah. But for this particular example, the only thing you care that there are nodes and there are apps, and just Kubernetes makes sure that these apps are running. Okay, next. So yeah, what Kubernetes does for you. So as I mentioned before, it makes sure your app is running. It gives you enough control to configure various different things, even advanced ones, such as auto-scaling your workload. Since in the previous example, you saw that there was the same app running across 2 nodes, so you can configure stuff like that quite easily. And yeah, in addition to that, it scales because lots of huge companies use Kubernetes. It's kind of a battle-tested thing, but if you are just a small startup where you just need one small single application running, you kind of don't care too much, I guess, about your scales. Okay, so where does actually spot instances fit in? So yeah, as on-demand is not always the answer. You don't need always the most expensive machine that is the most reliable. It's not required for all of the workloads. So spot instances kind of fit nice in that scenario. In addition to that, regarding the reliability itself, an orchestrator such as Kubernetes kind of does lots of the work for you. So if you look in the previous example where we kind of showed how a cluster looks like, in this particular example, you can see that's the same cluster, and it had additional nodes added to itself, which is node 3 and node 4. Both node 3 and node 4 are spot instances, and we are kind of hosting the app, which was app 2 and the node 1 first, which could be some sort of fault tolerant app. So, and it kind of needed some scale. Maybe it was Black Friday or something, and yeah, you just scaled up the app, and it used some of the spot instances to kind of host that, and you kind of wouldn't care much if these instances went down, since that app would continue working on its own, once more spot instances are back, or you kind of create an on-demand ones to replace it. Okay, so going next, it's a demo time. So let me try to switch to the browser window. Okay, try to zoom out. So yeah, in this particular example, we have a cluster running. So it's similar as in the screenshots shown before. So basically, it's a cluster with one master node and two worker nodes. And as you can see, like in this UI, one of them is just a spot instance. And if you went to the AWS console and checked the same cluster, you could see the nodes it has. And in this particular scenario, like as in the UI, you can see that one of them is the spot instance node. You can see that this instance has a spot marker as well. Yeah, it says lifecycle spot. Give me a second. Okay, it has lifecycle spot. So in the typical scenario, like when the spot instance interrupt would occur, like you would either kind of need for yourself to handle this thing and kind of replace the node with some other node, whether it's a spot instance or like some other kind of node. So you would kind of need to add another node to your AWS farm of nodes for your account. So let's just emulate the scenario. So what I would do next, I have a node running, I have a cluster running a spot node, and on that spot node is just deploy the dummy page. It's just basically an HTML page showing that this is hello world from the spot instance. So if I simulate the removal of this node the similar way as AWS would do if they were to interrupt your node, you would see like that immediately. It would take just a few seconds and your application is kind of like down and you don't have like anything to access. Just give me a second. It will take some time to reload here, but it's already kind of failing to load. So yeah, the node is being taken away from you. The URL is like not responding anymore. It's just like you can see it's loading here. Yeah, so the service is not available. So in typical scenario, if you have like no way to handle the fallback once your node is removed, you would end up not having your application online. And yeah, it's good that it's just an HTML page, so it doesn't mean anything. But when you just go to AWS and you can check like that the node is not here anymore and it's terminated. But since it is Kubernetes and we have this some basic features for auto scaling, what we are doing here, that we saw that the load was gone, the application had no place where it could run. So we are basically scheduling another node reacting to this interrupt, and in like a couple of minutes, the node that is being created, which is the new one, will be online, and your application should continue serving its content. Okay. Bear with me for a couple of minutes.
Sorry for interruption, Zilvinas. I think we see the same screen. Can you double check it?
I kind of changed that, but I can try to reshare again. Give me a second. Can you see it now?
Yes.
Browser.
It's a browser, and if I change something, you can see now. Yes?
Yes.
Yep.
Okay, so did you miss that part where I kind of deleted node? Did you see that?
In EC2 or in cast.ie?
In cast.ie, which basically resulted in EC2 removing the node as well.
We missed that part.
Okay, so let's try again. So basically what I did when the screen was stuck, I kind of triggered this node deletion. It was a different node at that time, and it caused the service going down. And yeah, let's just try it again. I will just delete the node. So as you can see, like the node is removed here, so it will take some time till it's actually like fully out of the system. It's also being outed by AWS as well. So yeah, I hope the screen is not stuck. So let me know if it's still stuck, since this is the relevant part. Since you can see that that machine is already shutting down, which basically means we have no place to kind of run our workload. So this application is still unavailable. So the idea behind that is that Autoscaler will just create a new instance which is required for this workload. And since the particular workload is marked as only to be runnable on spot instances, it will just try to create a spot instance one. And once it is back, you should be able to see the application running again. Yeah, it takes a little bit of time, so a couple of minutes. Yeah, it's already joining the Kubernetes cluster, so bear with me for a minute. As you can see, like in the screen, the application is still not running. It's still waiting for the node to join the cluster. And once the node joins cluster, you will be able to see the HTML content because it will have a place to be served from. And in particular scenario, you can even already see like a couple of problems. You can see that I tried to launch like 3 instances of this application. It has no place to be ran on, and it's already been like that for 2 minutes. So that wouldn't be a good thing, like if it was your production load. But we will talk about this, I guess, during the Q&A session more. So yeah, the new node is actually still in not ready status, but it's already joining since it's already visible in the Kubernetes cluster node list. So this is my terminal screen. Let's see if it's visible in UI. Okay, so UI says ready. In a few minutes, the application should start just fine, and it should show the content being served. Yeah, you can see the application is already creating because it has a target where it can be ran. So there are 3 instances of that. So it's already creating. It will take some time for this load balancer to be updated. Yeah, and as you see here, the application is back on the new spot node, which basically means you managed to create a new node, and Kubernetes managed to kind of orchestrate that your application will be run on this newly created node. So in this particular scenario, you can already see like lots of downsides, and you have like a 3 or 4 minute of window where your application is not running anywhere, and there are basically like many strategies to cope with that. But this is like kind of done part of a demo, and about the strategies I will talk like during the next slides and during the Q&A session. Okay, so let's go back to the slides. Okay. So yeah, there's usually like lots of strategies when using spot instances. So one of them, which I kind of forgot to mention in the previous slides, was where you saw a loop where the supply and demand grows. There's another thing that you can pass as part of the creation of spot instances, which is basically called the max price. What it indicates it is a max price you are willing to pay per hourly for your spot instance. So if it goes above some kind of amount that you are not willing to pay for a spot instance, AWS will just send you an interrupt and you will lose that instance. In addition to that, it's like a very important thing to cherry pick the nodes you're using. Whether it's advisor tool, your own experience, or something else, but advisor tool is kind of a nice one, where you can just go and check the less popular ones, since the less popular ones are of a lesser chance to be interrupted, and they're kind of meant to be ran longer. And like that, even during our own tests, we had like long periods of time of like several days where you wouldn't even receive an interrupt from spot instances. So even if at first glance they may seem like a completely unreliable thing, but they're like just kind of ways around, but you could make them reliable enough or good enough for at least partial of your workload. So whenever you receive spot interrupt or rebalance recommendation, there are like lots of things to consider which you could do next. So in our particular example, we just did the most simple one. We just got the interrupt, we saw that machine was down, and we just went on and created a new one, which basically had a downtime of a couple of minutes. But in the other scenarios, what you could do, you could kind of wait for rebalance recommendations. You would see that machine is at elevated risk, and you would kind of trigger creating a less popular spot machine right away. Or if your workload is a little bit more critical, or you're sure like that you are willing to pay a little bit more to make sure it will be running somewhere, you can just like spin up a on-demand EC2 instance as a fallback for that, since there might be times where you are requesting like a spot instance, but that one is not available, the one you want. So falling back to EC2 is kind of a nice option. Okay. So yeah, there are various options which you could do to kind of handle the scenario I just showed. So yeah, you can kind of try out Cast AI and just see how it works yourself. You can go to like some other competitors and do it. And yeah, even AWS itself has a bunch of autoscaler configurations available. But yeah, each of the companies are taking different approach at these things. And in our kind of in our side, we are kind of trying more of a multi-cloud approach where you can just take from any cloud farm and just join it into your pool of nodes, and we think it's kind of a good one. Yeah, and there are many others as well. So yeah, I guess that would be it with the presentation. We can go to the Q&A session if people have questions still.
Hey, Zilvinas, thank you for presentation. And there was a lot of questions, but most of them have been answered by either Leon or Victoras in the chat. So I'm not sure how we should proceed, because I see that the most of the questions are answered. So maybe we can do it like this. We can proceed with next presentation, and you and your team will be able to answer these questions in the chat.
Okay, I guess
What do you
makes sense.
think?
Yeah, I guess makes sense.
Because now it will be really difficult to select which are answered and which are not.
I actually see a new question from Audimus. His question is, how do you manage cleanup of the nodes when EC2 is taken from you and the nodes are not drained, removed from Kubernetes cluster in time?
How do you manage cleanup of nodes when EC2 is taken? At least in my practice, I didn't have such a scenario, like where we would not kind of finish cleanup after ourselves. We just receive the interrupt, and we know that this node will go away, and we kind of reconcile our state with what is happening in cloud. So basically means we are constantly checking our state against cloud and making sure like it's at the right state on our side as well. So it's kind of sync what goes both ways. So AWS reports what we're doing something, we go then back to them and double check what was done there.
Okay, so that means that you are constantly looking for dead nodes and cleaning it up, yes, from Kubernetes API.
Yeah, in addition to that, when the node is kind of reported to be having interrupt, we kind of like already track it in our system, and we are sure that it will go down. Yeah.
Okay. Okay, so I believe the rest of the questions can be answered in the chat.
Okay.
So Zilvinas, thank you for your presentation.
Thank you.
And now I believe we can continue with Avishai.
Cool, so I'm going to share my screen and we can get started.
Okay, thank you.
Second. Okay, here we go. So I'm going to say a few words about Q theory. This is about mathematics, but it's not going to involve any hard formulas and stuff like that, because really it's not important. What's important is the insights from the math. If you do want to look up more material about this, there's plenty out there on the internet, and I will also provide some links. The story of Q theory is basically that in the beginning of the 20th century, Cooper Lang worked for the Swedish phone company. And back then, they still connected people to each other using like actual wires, and they had to like connect them in the switchboard. And you had to wait for an operator to connect you. So he was hired by the Swedish phone company to optimize the shifts of the operators, like how many operators you need per shift, in order to minimize the amount of time that people had to wait in line for the switchboard operators. But since then, we actually used Q theory in a lot of other fields, for, well, obviously software engineering, but also in the design of checkout for supermarkets, theme parks like Disney World and places like that, airports and many other places, basically anywhere that you see a queue. So it's a very important mathematical theory, and it's basically a statistical modeling of how queues behave. So with that, I'm going to talk a little bit about statistics and distributions. But before that, let me introduce myself. So my name is Avishai Shalom. I live in Tel Aviv. I work for ScyllaDB. ScyllaDB is a company that makes the open source database Scylla. And Scylla is a Cassandra compatible and also DynamoDB compatible database that's very high performant and scalable. When I say high performant, I mean like about 10 times the speed of Cassandra, also with very very low latency, talking about like 5 milliseconds on the 99th percentile, usually even lower than that. And we frequently see machines doing as much as 1 million queries per second on a single node. So you can imagine what a cluster of those beasts can do. So if you're interested in that, go to our GitHub. Everything's open source. You can check it out for yourself. Very cool technology. So let's talk about what we're going to do tonight. So I'm going to talk a little bit about statistics and statistical distributions. Then we'll dive into Q theory. We'll talk a little bit about Litter's law. I don't think we'll be able to reach the practical applications part because we're not going to have too much time. I am going to talk about some practical applications and advice in the part about Q theory itself. So let's talk about distributions. So when you hear a number, let's say we talk about my height. So my height is 170 centimeters, okay? But that's not actually an accurate number because it depends when I measure, how I measure, and so on. So if you measured my height, let's say 20 times, you're going to get slightly different numbers. One time it's going to be 169, 169.5, 171, 170.2, stuff like that. And it's going to be a distribution around 170. 170 is actually my average height. So little known fact. In the morning, you're actually a little bit higher than in the evening. You actually get shorter by a few millimeters during the day. But it's not only because of the phenomena like this, it's also because of accuracy. We cannot measure things more than a certain accuracy, and there's always some kind of distribution. Now, this is also true for everything else, meaning that if you have a large group of things, then their attributes or properties will have a distribution. So in the population, you often see that there's a distribution of heights and stuff and things like this. And when someone says something like, okay, this has a latency of 20 milliseconds, there's actually a distribution behind this, and 20 milliseconds is an aggregate of that distribution, usually the average. We'll talk about that in a bit. Now, this has very significant and profound meaning because distributions are usually infinite. And maybe there's a very small chance of seeing a transaction with, let's say, latency of 5 seconds, but it will happen given enough transactions. So improbable results do happen, and statistics will refer to this as the law of very large numbers. Another way to put this is that in a city like New York, where you have 25 million people, 1 in a million event is something that happens every day. So if we could circle back to software engineering, UUID collision, for example, is something that's not supposed to happen at all, unless you have 1 million requests per second, and then you're going to see this every few days. So this is something that's worth keeping in mind. Now, when we talk about measurements of distributions, we need to remember that usually we give like aggregates of the distribution, and those aggregates are usable for something. They're designed to give us information about something. So it really depends what we're interested in. So usually we divide those to two, the aggregate effects and the particular effects. So for example, an aggregate effect would be a load on your server. The load is something that happens because of all the transactions you had during that time period, whereas the latency that the particular user experiences is a particular effect. They only feel that specific transaction that they are involved in. They don't feel all the other transactions. So the server would feel the aggregate effect, and the user would feel the particular effect. And therefore, we would need different measurements of the distribution to deal with the different sides of the transaction. So usually, when we're talking about load and costs and stuff like that, we would use measures like averages or sums. And when we talk about user experience, we usually use things like percentiles, which more accurately describe what the user feels. What's really important here is that there's no single aggregate that can capture the behavior of the distribution. If you want to get more information about how the distribution looks, then you need several numeric aggregates, like histograms or maybe a number of percentiles and so on and so on and so on. So the most commonly used aggregate is the average or the mean. And the problem with mean is that it doesn't, like we said, it doesn't describe the distribution, but it's also very sensitive to outliers. So it's actually hides information, especially when we're talking about particular effects. So no user actually feels the average latency. That it's not a thing. So you could have a user that experiences 10 millisecond latency, while your average is 200 milliseconds. And you can also have a user that experiences 20 millisecond latency with the same average. And actually, you have a lot of very different distributions that would have the same average of the distribution. So just saying that the average is something doesn't actually tell you anything about the distribution, what users experience. So we usually, when we talk about latency, we try to avoid mean and average, especially if certain values have very dire consequences. So the example that's kind of violent I always give is that if I shoot someone in the head 1,000 times and I hit them only once, so in average they're alive, but in practice they're dead. So you can use the same example with server errors or things like this, but you get the point. Now, distribution has certain width. So certain distributions are wider, certain distributions are narrower, and we have some kind of a metric to describe that. And usually it's one of the variability or dispersion metrics. So most people know standard deviation, but there's a lot of other ones like variance, interquartile distance, and so on. I'm not going to go into that, but there's a reason why we have several different measurements, because certain measurements are not usable for certain conditions. Distributions, because they're infinite, they can go on and on and on. So you can actually get numbers that are very, very high and very extreme. This probability of this might be low or high depending on how wide the distribution is. But the systems that we work in computers are not infinite. So if, for example, you have a transaction that got delayed for some reason, maybe the packet was queued up in some router along the way, or maybe that there was a packet drop or whatever, this is going to translate into an error. So what we have is a cutoff, which basically means that if a value goes over a certain, if something goes over a certain value, we basically time out or we cut it off. and we return an error instead. And this is how we deal with the conversion from an infinite distribution to a finite system. So when we're talking about the width of the distribution, it's very easy to make a distribution wider, but it's very hard to reduce the distribution. And this is a problem because this variation, large variation, is a very big problem in software engineering, as we'll see in a bit. So what happens when you have high variation? So let's take an example. Let's say that you want to get from Paris to London, and you have a train, and the train takes 2 hours to get from Paris to London, but the train can sometimes be delayed, and the average delay is 15 minutes, but the 99th percentile of the delay is 120 minutes, like 2 hours, and the 95th percentile is 60 minutes. So what time should you leave the house if you want to arrive to London by noon, by 12 o'clock? So of course, that depends on your SLA. What's the probability that you want to be sure that you're going to arrive by noon? And let's say that the probability that you want is 99%. So you have to leave the house at 8 o'clock, 2 hours before. 2 hours before. Why? Because there's a chance, 1% chance, that the train will be as late as 2 hours. So what's going to happen is that most of the times, actually 99% of the time, the train is going to be delayed less than this. So you're going to waste a lot of time just waiting, not doing anything, but you have to do this because otherwise you might be late. So if you sum up all the times that you will, all the time that you wasted waiting for the train, so you will find that on average you wasted 105 minutes like every time. Just to avoid being, this 1% chance of being late. So this is the problem, basically. When we're talking about utilization, the higher the variation is, the lower utilization you can have. You have to take, a lot of spare capacity in order to avoid, getting into those extreme events. And that's a very big problem in software engineering. So because of this, and we have to design our system such that we basically, do over capacity and over provisioning all the time. Now, this problem is being aggravated by the fact that we often parallelize work. So if you think about things like MapReduce or fork join, where you have a parallel part and a serial part, and the serial part has to wait for all the parallel parts to complete before it can do its work, then it's going to wait for the last one. And that means that you're very sensitive to high percentiles, meaning that if you have, let's say you're waiting for 100 workers, there's a very good chance that at least one of them will hit the 99th percentile. So the time it takes to complete this work is going to be very, very long because you're basically going to experience the high percentiles. And similarly, customer satisfaction follows the high percentiles, because if you look at a web page often has a lot of assets and a lot of API calls that it has to execute. So if you have, let's say, 100 API calls that you have to do, there's a good chance at least one of them will hit the 99th percentile. And actually, Gilton did very nice statistics about this, and he showed that for the I think he tested like the 100 of the most popular websites on the internet, and he showed that for most of them, there's a good chance, actually higher than 80% for some of them, and for all of them, I think it was higher than 50% of encountering at least one 99th percentile. So that's a big problem. It means that the customer satisfaction follows the 99th percentile, or depending on what SLA you want to provide, but the high percentiles of latency and not the average. And similarly, disasters usually follow tail behavior, extreme events, things that are very rare that we can't have planned for, or that result in some kind of timeout or cutoff. Now, when you have a cutoff, let's say timeout, then you have to somehow do a retry, and you still need that work. And that means that you're going to generate more load because of things that have been outside of the cutoff. So the higher the variation, the more of those problems you're going to have, the more capacity you're going to waste, the longer group work is going to take, the more failure demand you're going to have, and so on, so on, so on. So high variation is actually one of the biggest problems in software engineering, which is why when we're building systems, we always try to reduce and control variance as much as possible. Sometimes we capitalize on variance. For example, when we design systems and we choose different hardware on purpose because we don't want correlated failures. But most of the time, especially when we're dealing with capacity and performance, we're trying to reduce variance as much as possible. So let's talk about queues and how this is being expressed in queues. So first of all, queues are everywhere. Of course, when you're talking about queue systems like RabbitMQ or Kafka, things that are obviously queue, then yes, you know you're dealing with the queue, but actually you have a lot of hidden queues inside of systems. For example, in Java, executors actually have a queue inside, futures also have a queue inside, sockets, they have a queue in the kernel, but still they have a queue. Locks behave like a queue if they don't actually have a queue. So that database connection pools is a very common example. Callbacks. So in a synchronous system, you have a callback queue that's attached to the scheduler, the event loop. So all of your callbacks are basically waiting in a queue. And of course, anything that's asynchronous, deep down somewhere, there's a queue. So it's very important to understand how queues behave because you're going to experience it in a lot of places in your software. So what is a queue? A queue is basically a buffer that's attached to a service center. So you have some kind of worker, which we call a service center, and it services the work that's coming from the buffer, from the queue, at a certain rate. We call that the service rate, and of course it has some distribution. So we can make assumptions on this distribution to model it, but and we have different models for different distributions, but generally speaking, this is the model. Now, work goes into the queue also at a certain rate and with a certain distribution. We call that the arrival rate. And we take work to the service worker from the buffer using a service discipline, which is basically a strategy of when and where we pull the work. So the obvious ones is FIFO, first in, first out, and LIFO, last in, first out. But we also have more advanced ones like priority queue, and of course some weird ones like Israeli queue, which is basically that when you put a work item out, you take its friends with it. If you have been to Israel, you'll understand why it's called an Israeli queue. It's actually useful for some things. The latency that we experience is actually constructed from two things. The amount of time that it takes to service the work item, meaning to handle it in your software, and the amount of time that it has to wait in the queue before it gets serviced. So the latency is actually an amalgamation of two things. And one of the assumptions of the model is that service time is independent of the queue, of the buffering. So this is the most important part of the lecture, and if you take something from this lecture, then this is what you should take in this graph. So this graph describes what happens to queuing latency when utilization grows. So on the x-axis, this is the utilization axis going from 0 to 1. 1 is like 100% utilization, and you can see that the amount of weight in the queue grows in a non-linear fashion when you approach maximum utilization. So when you get over, let's say, 75% utilization, it starts to shoot up very, very quickly. And that means you're going to experience latency that can be even infinite. Of course, you're going to get timeout at some point, but you get the point. So as a rule of thumb, we always recommend that you run your systems at less than 75% utilization. Of course, there's more to it. We'll talk about that in a bit. But it means that we always have to have overcapacity if we are to control latency. Now, the units here of this graph are proportional, meaning it's proportional to the service rate. We'll talk about this in a bit. So this is not milliseconds. Now, the link here on the left side, if you want to take a look at this, is Cumulator. Cumulator is basically a visualization of those graphs, and it allows you to play with the parameters and see how it behaves. I'm going to show it in a bit. So let's move forward. Let's move forward. Cool. So why is this happening? Why are we experiencing such rise in latency? So the problem is this. When we have work going into the queue, and let's say the service center is not doing anything, it will take the work immediately and you're not going to wait. But if for some reason, it was delayed, because remember, there's a variation in the service rate. So sometimes it takes a bit longer to service a certain item, sometimes it takes a bit less. So, and also items are coming into the queue at some variation. So sometimes you would get 5 items, sometimes you would get 2 items, sometimes you would get none, and it changes. So if by some fluke of events, maybe the service center got delayed a bit, maybe you got too many items at the same time, then you would start having delays. You would start accumulating, items waiting in the queue. However, if the service center is working, very fast for whatever statistical reason, again, by chance, you're not going to gain anything because you cannot save the free time. So it's basically a lose-lose situation. If you got delayed, things will queue up. But if you're ahead of the work, then it's basically wasted. You're just wasting time. You're sitting idle, and you can't bank it. So it basically means that you can only lose in this situation. So on the right side, we see this is like the microscopic view of the queue. So this is what goes on in the queue, and you can see that the queue size fluctuates very heavily, and sometimes it just shoots up very, very rapidly, and then it takes a while to drain the queue, and then it might shoot up back again. And the thing is that that this is the situation in almost all queues. So usually, and this is a personal hobby of mine, when I go to a cafe or a supermarket or whatever, I just look at the queues, and you can see that the queues are almost always either full or near empty. They're not going to be completely empty. There's going to be like an average queue length, like we discussed. But when something happens, they fill up really, really quickly. So you might see that maybe the cashier is checking her phone or getting a phone call, or someone's calling her or whatever, or there's a problem with the computer, whatever, and suddenly there's like a large queue forming up because a bunch of people went to the store and now you have a queue, and it takes a while to drain that queue. So what are the implications of this? First of all, you should never have an infinite queue. Why? Because if for some reason you had a statistical delay, then a queue will form up and you will start wasting memory. You will start consuming a lot of memory. And if you have an infinite queue and maybe your service worker is now too slow, then you might expend all of your memory and you might go into out of memory condition or memory pressure and garbage collection, stuff like that, like this. This is actually very, very frequent. This happens a lot. I've seen a lot of systems that had this problem. Why? Because by default, a lot of drivers and a lot of runtimes like Java, for example, Java executors, little known fact, they allocate an infinite queue. So it's recommended not to use the default constructor. But I've actually personally found bugs in various drivers where they used internally infinite queue, and this caused out of memory for various reasons. So that's a problem. But even before you get out of memory, you're going to experience very high latency because of what we call the head of line blocking. So if you have a FIFO queue, then the last item will have to wait for all the items before it gets serviced. So basically it's going to block until the head of the line is cleared. This is why it's called head of line blocking. And it means that you're going to experience high latency long before you get to out of memory condition. And also, if you have an item that's waited long enough to queue, by the time you service it, it might not be relevant anymore. Maybe the client has timed out. So there's really no point handling this item when no one's waiting for the answer anymore. So that's a problem. So you should always, always, always limit the queue size. And if you are using very large queues, then consider using a TTL expiry on your work items, just so you don't handle them if they're not relevant anymore. Now, going back to our equations, this is the equation for service time in terms of time, milliseconds. So if you look at this, you see that the delay is actually relative to the service center, which means that if the service center, meaning your service, is slower, you're going to experience higher delays. Okay, so as an example, let's say that you're running a service with 50% utilization, it's going to experience 200% queuing latency. So if we're talking about a service that takes, let's say, 10 milliseconds, then the queuing latency that's added on top of the service time is going to be 10 milliseconds, which is like, that's not good, but it's not horrible. But if you're running a service that takes 100 milliseconds, the delay is going to be another 100 milliseconds, which is a lot of time. Okay, so the lesson here is that the slower the service, the higher the queuing latency, which means that we have to over provision more. So So when we have a system that's comprised of multiple services, the service with the slowest service will have to run at relatively lower utilization than all the other services. So I'm going to switch to Cumulator for a second and show you this. So this is the MM1 model. And this axis here is this bar. I can play with the service rate. And I can make my service faster or slower. So on the right side is slower, and on the left hand is, sorry, on the right side it's faster, on the left hand it's slower. So if I make this in the service faster, you can see that the latency curve is getting better. And if I make this service slower, you can see that now the latency at high utilization is pretty bad. So if I want to run a service at high utilization, I need to make it faster. I need to make it even a lot faster. And you can actually see that, for example, if this is, let's say, at requests per second. So if I have 6 requests per second, I'm going to experience 25% of the queue latency. Whereas if I run it at 1 request per second for the same amount of utilization, I'm going to experience 1.5. So 150% latency increase. So going back to the presentation. So the other problem is that utilization is also not constant. Let's say that you're running a service at 50% utilization. You will have shifts. Utilization, maybe after a few minutes will jump a little bit and it will go down a little bit. So 10% fluctuation at 50% will take you all the way to 55% utilization. This translates to an increase in latency of 1.1, meaning about 10% from previously. But if you're running a service close to the edge, 90% utilization, a 10% fluctuation will take you from 0.9 to 0.99, which translates to a 10-fold increase in latency. So you would go from, let's say, 100 millisecond latency to 1 second. And that's a very big difference. So it means that to run a service close to the edge of utilization, you need to have very stable utilization. You cannot have highly varied utilization. So you have to be very, very careful. And if you want to run a service close to its maximum utilization, you have to cap the load somehow. You have to make sure that it doesn't fluctuate too much. So this is the Kingman formula, and this is an extension of the previous formula to include the effects of variation. And basically what we can see in this formula is that the higher the variance, the worse the latency utilization curve gets. So I'm going to switch to Cumulator to show you this because it's easier to observe there. Second. So let's switch the model to Kingman. And here I can play with the service and arrival rate variation. So usually you cannot control the arrival rate variation. It's usually determined by the clients. And usually you don't control the clients, again, depending on your systems. But let's play with the service rate. And as you can see, when the variation of the service rate goes up, the latency curve becomes worse. So for example, the blue line here is my high variation curve. You can see that even for 70% utilization, it's already a lot higher. It's about 5 times higher than normally. And this is also sensitive, of course, to the service rate. So If the service rate is faster, then the entire utilization curve is going to be better. So my options are as follows. If I want to run a service at high variation, I need to make that service faster, or use a lot of overcapacity, so I will be in a more stable part of the curve. Alternatively, I can just make the service somehow have lower variation, which will also improve my curve. You see how the blue line goes down and down and down, because as I'm improving the variation, as I'm making the variation smaller. So another way to look at this would be to look at the static lines here. I plotted them for different variations. So you can actually see that when you have higher variation, the lattice curve becomes worse. So what's the practical advice here? What can we do to control this? First of all, use choke points. So what is a choke point? A choke point is basically a defense mechanism. It can be a proxy. It can be a throttler that we introduce in the outer layer of our service. Usually the good place to put this is at the edge of the system. And what we do in the choke point is basically we cut off the excess load. We don't want to get, we want to control basically the input load. So there's two ways to do this. One way is throttling, the other way is load shedding. The difference is basically whether we control the rate or we take a queue, and when that queue is too full, we just drop everything out of the queue. So we have like a capped queue. That's the two basic ways of doing this. And why do we want to do this? Because when we plan for a certain utilization rate, and we don't want to exceed it. So this is how we control it. The other thing that we need to do is capacity planning. We need to plan our utilization, and when we have a resource that's slower, maybe it's a disk or a service or whatever, we have to over-provision it more relatively to the other services of the system. Now, of course, if we want to run things at higher utilization, what we need to do is A, make our services faster, and B, lower the variation of the services. That's basically our choice. We need to do either one. So if we cannot improve the variation, we need to either run it over capacity or make the service faster. If we cannot make the service faster, or maybe we don't want to, then we need to reduce the variation somehow. So this graph, for example, is a comparison of Scylla with Cassandra, and Scylla, because it's faster, and B, because it's more predictable, meaning its variation is much lower than Cassandra, can actually drive a system close to 100% utilization, whereas Cassandra, you would usually run it around 70% utilization maximum, because it's very, it has a high variation in its latency curve. So when you have a system that's comprised of multiple services or multiple parts, one of the problems is that you have internal queuing. So you could have a queue building up in the middle of the system or deep inside the system, and you would still have load coming in from the outside because the client doesn't know about this. They don't know that they should stop, injecting load. So what do we do in this situation? We use a tactic called back pressure. So we basically want to let our client know that we cannot take any more load. We're overloaded. We went over our design utilization. So we apply back pressure. We basically tell it to stop. There's a number of ways of doing that. And in turn, it will also say to its client, hey, I'm overloaded, stop. And it will basically transmit the message through the chain until the original client will know that somewhere down inside, things are out of capacity. So a lot of the protocols actually support this. For example, HTTP has the 503 response, which is basically upstream, like normal capacity in the upstream. So when you send 503 to a client, it's supposed to throttle itself and stop, issuing more and more requests. Another way to do this is use a blocking client. Anything that's blocking applies back pressure by default. So you would block, your client would block, and so on, so on, so on. And when we're talking about thread pools, the way to do this is to use finite queues because the queues themselves are blocking. So when the queue is full, the client that is trying to put work in the thread pool will block, and so on, so on, so on. So if you're using blocking code, threaded code, then you have back partial control by default. You just need to make sure that you don't provision too many threads. But anything that's asynchronous, like executors or remote calls over the network, or sync code like in Node.js or Netty or things like this, will need explicit back partial mechanisms. There's a number of mechanisms for this. Reactive streams, if you know what it is. If not, look it up. This is one of the ways to do back partial in a synchronous system. Now, if you want a very common example of a system that doesn't have back partial by default and can have a problem, Kafka is a very good example. If the consumer, for some reason, lags behind the producer, maybe the producer became too fast, or maybe the consumer became too slow, doesn't matter, then the queue in Kafka will build up very, very fast because there's no back pressure. No one tells the producer to slow down. So once we have back pressure in place and the edge of the system now knows that there's too much backlog queue building up in the middle of the system, we can do something useful about it. We can load shed, as we said before. So load shedding is basically a trade-off between queuing latency and errors. So we don't want to have queuing latency, so we don't want queues building up inside. So instead, we return error. And one of the common mistakes is refusing to return errors. A lot of times, developers think that returning errors is not a good thing, and usually you would be right, but you want to avoid overload and degradation of service to all of your clients. In order to do that, you need to return errors to the clients that are overloading your system, basically. So this is a trade-off that we have to do, and you have to decide when your system is overloaded, what do you prefer? Do you prefer having excessive latency to everyone, or do you prefer that people that will get service get predictable service and good service and return error to everyone else? So that's a choice, basically. And as I've mentioned before, the way to do this, we can either put a queue that has a finite size and cap it, and return errors to anything that doesn't fit in that queue, or we can throttle using usually a counter and say that let's say in 1 second we can this work you can only do 10,000 requests, and after this counter is hit 10,000 for this particular time window, we just throw all the requests and give them an error. So we don't necessarily have to return an error. There are alternatives. For example, we could give degraded service. For example, you could serve a cached version of the website. You could return less accurate results. It really depends on what kind of service you're running, how to do this. So if you're running, let's say, a recommendation service, then you could use a faster, more naive algorithm that gives results that are not as good, but it's a fallback. So instead of returning errors, you would just return results that are not as good. So you don't necessarily have to return errors. It really depends on the business. So sometimes you have other options. So let's talk a little bit about Litter's law, and then I'm going to break for questions because we don't have too much time. Litter's law is something that you're probably already familiar with in some form, but maybe you haven't heard it as a mathematical law. It's a law that's universal. That's why it's very powerful. It applies on all distributions. And this is also the reason why it was actually very, very hard to prove mathematically. It holds for stable systems. I'm not going to go into the mathematical definition of stable. Let's just say that if your system changes slowly enough relative to the rate and the latency, then it's stable. Now, what does this law mean? Basically, the law means that the amount of clients inside of the system is equal to the average amount of clients inside the system is equal to the average throughput times the average latency. And when we say throughput, in this case, we mean the arrival rate. So if you compute this for a system, you draw a system on a paper. So the edge of the system would be where you compute Litter's law, and the arrival rate is anything that goes from inside into the system. And the clients inside the system is basically everyone inside of the system. Now you could do this iteratively, meaning that you could divide your system into parts and you could compute Little's law for each part in the system. And this helps you do a lot of cool things like debugging, for example. If you can, usually the throughput would be the same for the entire system and the latencies would be different. And this allows you from two metrics that you usually have for all the different parts, let's say a load balancer, a proxy, an application server, a database, and so on, you could actually compute where clients are waiting because you have the number of clients in the system. So let's say you have 100 clients in this system, and then in the subsystem you have 50 clients, then you know that here somewhere 50 clients are waiting, and you know that this is the problematic part. So this is why this law is very useful. Another reason why it's very useful is because we can use it to debug benchmarks and things like this. So to understand this, we should talk about correlated clients. So usually we have two different types of systems. So remember, we have three variables in Little's law. We have the number of clients in the system, we have the throughput, and we have the latency. So latency is usually a property of the service center and the queuing, like how much queuing you've experienced. So it's not a free variable. So what do we control? It depends on the type of system. On a web system where we have a lot of independent clients, let's say a lot of mobile phones or a lot of browsers or things like this, they are uncoordinated with each other, they're independent, and therefore the throughput is the free variable. Okay, this is what they control. And the number of clients in the system is derived from that. It's basically the response, it's determined by the response of the system. In contrast, when you have a system like a thread pool or a load testing tool or something like that that generates the traffic, then the requests are dependent. If it's a load generation tools, the dependency is by the thread pool inside the load generator on the load generator. So this means that the free variable in this case, not the throughput, it's actually the concurrency, the number of clients in the system. And it means that the throughput might deviate from what we planned because of this coupling between the clients. So what this means is that in many cases we see that load testing tools don't give us good, accurate results. They give different results from what we see when the system is actually in production. And why? Because it's two different systems that behave in a very different way. And how does this relate to Little's law? What we do with this basically is we use the Little's law to validate the results of load testing tools. And when we do this, we often find that the results of benchmarks and load tests are broken. For whatever reason, usually it's because of an overload in the load testing tool. It couldn't produce the necessary concurrency for the test. And therefore, the throughput that it actually generated deviated from what we requested. So there's very interesting articles about this on the internet. I put some links on in. Other things that you can do with Little's law. So for example, let's say that you want to calculate latency when you don't have direct measurement available. One of the big problems, for example, is knowing what is the actual latency that your client experiences. If you have a client that's a mobile device or a web browser, it's very hard to get telemetry from the client side. So the only way to get some measurement of the latency would be indirect. And how do we do this? If we know the throughput and we know the amount of connections that we hold to the clients, then we can compute the average latency. Of course, we would want to know the 99th percentile, but that's impossible. So we, we get what we can. So average is sometimes the only thing that we can get with some reliability. So this is an example of doing system analysis with Little's law. So this is a system that has, let's say, 10 servers, and those 10 servers are connected to a load balancer. And the load balancer usually uses a very common algorithm, which is least connections. So basically, it would, when it receives a new connection, it will send that connection to the server that already has the least amount of connections that it's handling. So basically, it's a system that tries to balance concurrency or clients in the system. So we can use Little's law to analyze this because L, concurrency of the system is, users in clients in the system is the variable that's supposed to be equal because of this algorithm. So we can plug it into our equations, and we can see what happens when the relative latency of servers change. So let's say that one of the servers had a problem. The database failed, for example. It cannot connect to the database for whatever reason. Maybe its client failed, or it has a network problem. And now it would start returning errors very fast. So let's say that the latency before was 100 milliseconds, and now it returns errors in 1 millisecond. So by Little's law, we can see that the throughput will grow 100 times in like a factor of 100. So this single server will receive the same amount of traffic that 100 equivalent servers would receive. So if you had 10 servers, you would expect to have 10% error rate when a single server fails, but instead you would receive something closer to 99.9 error rate from the failure of a single server. So this surprises people because you don't expect failures of a single server to take your entire system down. Like, the reason why you have multiple servers is to avoid exactly this. So it's very important to understand. How do we avoid this? One of the ways to avoid this would be to change the algorithm of the load balancer. We can change it to something like round robin or random, which are algorithms that basically balance throughput and not concurrency. And this solves this. Of course, those algorithms have different problems because everything is a trade-off in engineering. So that's one of the ways. Another way would be to have throttling inside of the load balancer so it doesn't send too much traffic to a single server. But this means that you have to know or cap in advance like how much throughput a single server can take. So, but most of the load balancers support this. So with this, we're going to break for questions. And if you're interested in learning more about this, so there's a lot of recorded talks. I've actually talked about this subject for a few years now, and there's a lot of other people that talked about this. And of course, there's a lot of academic material about this as well. So now I think it would be a very good time for questions.
Yes, so thank you, Avishai. We have a few questions, and these questions are posted in Zoom chat, so you can check it out.
Okay, so let's see. So let's take it from the top. So another questions, it assumes that request handling depends on the remaining capacity. Is not changing if certain bit increasing the loads does not impact service time? I'm not sure I understand. If I understand correctly, the question is the model, does the model change if the load does impact service time?
The second message from him is a follow-up to that question.
Okay, so you have a lot of spare capacity in 10 nodes, so maybe increasing the load won't make subsequent requests any slower. Okay, so the thing is that in many computer systems, especially when you're dealing with shared capacity, for example, on Kubernetes, you have a problem that you have different levels of queuing. So for example, the operating system itself has a queue, the scheduler queue. And for this reason, even like if the overload was, let's say, on the thread pool side of the, let's say, application server, you can still hit another queue, which is the operating system queue that's, let's say, also overloaded. And that means that you're going to experience even more severe delays because you're actually overloaded in two different places. So it's actually like a more complicated model. The model that we use for this is called the queuing network. It basically models the interactions of a number of queues and not a single queue. But the results would be similar to this, although the details might be a little different. I hope it answers your question. If not, then let's get follow up. So another question, Java is oftentimes benchmarked to be as fast as C++. Would you say that the low variation speed improvements provide mentioned. Okay, so the question is
This one, Avishai.
the reason, what, sorry?
This one was related in your slide when you showed Cassandra
versus Scylla.
Yeah.
So the answer is yes and no. Actually, the reason why Scylla is 10 times faster is not only because it's in C++ and the variation is lower in C++. It's also because Scylla actually has a very unique design, shard per core design, that is basically is built to minimize the queuing on the operating system side. So Scylla is based on a framework that's called Systar, also open source, check it out. And it's basically a miniature operating system. So it actually overrides a lot of the functions of operating systems in order to provide this performance. And it basically avoids the operating system level queues that Java would necessarily hit. And it manages I/O itself to avoid the disk queues also, and actually has a very interesting auto-tune that tunes to the concurrency of the disk, again, to avoid queuing delays on the disk and a lot of other stuff. So it's basically the reason why it's 10 times as fast is not necessarily because it's in C++. C++ is necessary to support this kind of architecture, but it's the architecture that brings this speed, not the language per se. So I hope that answers it. If not, we have a number of lectures on this topic. Another question, what is the common practice to introduce backpressure in microservices world with hundreds of interfacing services? How to tune so many parts? So that's a very good question, and warrants a completely different talk. The answer to this is, first of all, to build it into the protocol. So if you're using something like gRPC or HTTP or something like this, then backpressure is already built into the protocol, and all you have to do is to make sure that the services that you build don't break this. You need to make sure that they support this. There's a lot of ways to break this. For example, having a service that has no limit on concurrency. Maybe you're writing a service in Node.js and it doesn't, Node.js doesn't have any limit on concurrency by default. So you're breaking this promise of backpressure. But as long as you keep this promise of backpressure, then you will have this coordination automatically between your different services. So the infrastructure for this is already built in. However, it does get more complicated in a certain sense, because I also talked about over-provisioning. And over-provisioning is a little bit harder to manage because, first of all, latencies can change over time. So even if you have a certain over-provisioning target, it might change. And second, because of various failures and conditions that you can have in such a big dynamic system. So if you have a system that has some kind of auto-scaling, then on the upside, it can adjust itself to the required over-provisioning capacity. But on the downside, it can also generate failures because of, let's say, miscalculation of the same thing, especially if you haven't controlled your concurrency. So the answer is that A, it's complicated, and B, there is support in the protocols and frameworks for this. The biggest problem with this is actually things like Kafka. It became very popular to connect microservices through Kafka. And with Kafka, because there is no backpressure by default, if you're not careful, it's very easy to knock your entire system down. So any more questions?
I don't think there are more questions at the moment. So thank you, Avishai, for a really interesting topic and quite a deep one. So now, if you let me share the screen.
Yeah, let me exit. There we go.
Yeah. Okay, so now we'll have a quiz coming up. So in quiz, we'll have questions about the Zilvinas and Avishai presentations. And for this, we'll have a separate Zoom meeting where you all have to join the Zoom meeting. And down there, will have questions showing up, and you'll have to use your mobile phones to answer the questions. You don't need to install any kind of applications. We'll use Kahoot for it, so you'll just need to visit our website. And we have prizes from our sponsors, bookstore vouchers, Monzo gift cards, and from CastAI CPU resources on the cloud. So the links for the joining are in the Meetup website comments. So please join there. And that's it.